All right, ladies and gentlemen, class recording has started. So, today we start in on the last section of this unit on acceleration, and that deals with falling objects, or the acceleration caused by gravity. That is going to start with this picture. So here's a picture that is a time-lapse picture of two objects, and from the picture of these, from this picture of these objects, you should be able to tell me a couple of things about the motion of those objects, either individually or in relation to each other. So what I would like you to do to start off is take 30 seconds and talk to the person, next to you, in front of you, behind, whatever, about these pictures and the motion that it is representing, and see if what you can come up with about this motion based on this picture. 30 seconds. Talk. Go. Let's discuss. So, just because I heard it up at the front. So, John, what's the first thing that you said about the motion of these objects that you can tell that they're doing?
They're accelerating.
Okay, how can you tell that they are accelerating?
Because at each interval, it's getting further apart.
At each interval, each picture, right, if we assume they represent a equal amount of time, the pictures keep getting farther and farther apart, indicating to us that they're probably going faster and faster, right? And so that can be accelerated motion, all right? What else? Anything else that you guys came up with in discussing? Did most of you come up with this at least?
I just had 9.8 meters per second squared.
We don't exactly know that from this picture, but we'll introduce that number soon enough here, right? But from the picture, a couple other things that we could probably tell. First, these two objects have the same velocity. How do I know that they have the same velocity? Because they're even, right? They keep staying right next to each other. Now, that velocity is changing, but they still maintain the same velocity because they're right next to each other, right? And then the last thing, while they are accelerated, right, this is accelerated motion, we could say that the acceleration of these objects is the same. Because if we look at the intervals for the apple, right, especially if we look at from the bottom of the apple, right, the same spot, we would see that that spacing keeps getting bigger at the same rate that the spacing for the feather keeps getting bigger. Okay? Good there? This happens under circumstances where gravity is affecting the motion of that object, because we have come to realize over, years and years and years, that gravity accelerates all objects at the same rate. Gravity will affect or accelerate all objects at the same rate. Okay? And then, Maxie, here on Earth, that rate is what?
9.8 meters per second.
Okay. That here on Earth, that acceleration is 9.81 meters per second squared. That the gravity here on Earth causes an acceleration of 9.81 meters per second squared. So, pulling some things out from previous topics in this unit, if we say something causes an acceleration of 9.81 meters per second squared, what does that mean?
Probably speeding up.
It could be, right? Because we said that acceleration has how many forms? Three forms, right? So let's start with that one, right? If something is accelerating at 9.81 meters per second, that means it could be doing what?
Speeding up, slowing down, or changing
Well, let's go with the first one, right? Okay, so let's take a situation where, all right, so here's my hand, right? Okay, not the best hand in the world, but whatever. And here is a ball, all right?
Great circle.
Thanks. It's a perfect circle. I would draw nothing less than a perfect circle, obviously. So, but anyway, so I take this ball, right, and I drop it. Well, actually, I found this out. It's not really. I'll save it for the next part. Okay. But so I drop this ball, and as I drop this ball, what's going to happen to it?
Speed up.
Faster, 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 right? So we'll indicate that it's speeding up like this. At the moment that I dropped that ball, when it became under the influence of gravity, what was it doing at that very instant?
Accelerating.
Yes, that would be more how it was changing. What was it doing? So that means that, so Cal, if we say that it's rest, what can that tell us, like, variable-wise, we would say here? Nah, it's a crappy question.
Velocity is zero.
Okay, that's what I wanted you to say, but I asked a bad question. So. All right, so I let this object fall for 1 second. How fast is it going now? Its velocity now is going to be 9.81 meters per second. Why? Because what did we say the acceleration of this object was?
I said it was 9.1.
We said that gravity on Earth causes an acceleration of 9.81 meters per second squared. Remember earlier in this unit, we said that an acceleration of 9.81 meters per second squared is the equivalent of stating this, right? That for every second that goes by, this object's velocity is going to change by 9.81 meters per second. That good? On a somewhat unrelated topic, although not totally unrelated, if I measure this distance, how far it falls in 1 second, will that be 9.81 meters?
Yes.
No.
Yes.
Anybody else want to weigh in? Or?
Yes.
Do we say again? In that 1 second time period, will it be 9.81 meters? Will it fall that far?
Yes.
No.
Yes. Yes.
Looking good.
I was gonna say it reaches 9.81 meters per second at the end of its function.
Right. We talked about, remember the balls on the ramp that we talked about, right? It reaches 9.81 meters per second, but not until the end of that 1 second interval. If it was going to go 9.81 meters in 1 second, it would have to be going this speed the whole time. And it's not going that speed the whole time. It's gradually building up to that speed. So it won't go 9.81 meters, even though that's how fast it ends up going eventually.
So what would be the square root or divide by 2? or
Well,
something?
we could do this, right? So if we look at this red trip, right? We want to know this, right?
Yeah.
So what else do we know about that red trip? This is getting into a little bit of a kinematic
We
picture
know
problem.
VI and V final.
Okay, so we know VI is what?
0.
And we know that V final is
9.81.
9.81, right?
Divided by 1.
And then we also know that it's
1 second.
1 second, right? So do we have enough information to plug this into a kinematic equation?
Yes.
Yeah. What we would find out is that actually it would be 4.905 meters.
So it is divided by 2.
Yes, in this case, because we're only dealing with 1 second,
second, yeah.
right? You know, that won't be the case each second later on because it keeps going faster, right? So that relationship only holds for the first second, not for the whole time. Okay? All right, are we good with that? Next situation. Because we said gravity causes an acceleration of 9.81 meters per second squared. So we just talked about a situation where gravity can cause an object to go that much faster. But what else can gravity do? Make it go that much slower, right? Sure. Right, so there's my hand again, right? And then here's my perfectly circular ball, all right? So watch this. I just learned this last period. I'm not going to joke. I did not know this was going to happen, right? We ready? So we take this ball. Oop. So we take this ball. You can watch it on the screen too, you know. So we can take this ball and throw it into the air. Oh, and it like stops automatically. You see that or no? Come on.
Do it again, do it
Here we
again.
go. Okay, ready? Here we go. We're gonna take the ball, right? And we're gonna throw it. No, not enough. So take this ball. We're gonna throw it into the air. I did that in the last class, and I didn't know that was gonna happen, and I was like. But regardless, so let's say I take and I throw this ball into the air. When it leaves my hand, I threw it with a speed of 9.81 meters per second. That's how fast I threw it. How long does it take to get to the top? Like 1 second. Okay? In fact, how do you know that? You gotta explain to me how you know it. Not exactly, but kind of, right? Okay, because at the top of this motion, what does it have to do? Well, before it changes direction, it has to do what? It has to stop, right? So V final here is now equal to 0. So is it the same thing?
No, it's just flipped.
Not exactly. It's like flipped over, right? Gravity's causing it to speed up on the way down, but it causes it to slow down on the way up. The same amount, though, right? The same amount. Good there? Ah, good question, Anthony. Glad you asked that. Right. So now, let's say this. Let's say a different situation comes along, and this time, when I throw it, I only throw it with a velocity of 4.905 meters per second, which we said is how fast as the first time. That's half as fast, right? How long is it going to take to get to the top this time? It's only going to take half a second, right? But is it going to be up here?
No.
It's only going to go how far? Right? It's only going to go this far. Okay? But now this would only be 0.5 seconds. Okay? Because we said that this acceleration, it changes by this much every second. Oh, it's like, it wasn't my fault. That's all right. The velocity changes by this much every second. But to get it to go from 4.905 to 0, right, is only half this much. So it's only going to take half the time. Now, here's the next question. When the blue one is up here, where's the red one end up? Logan says back at my hand. Because, Logan, right? How much of this did it change in half a second? Half of the 9.81, right? What's gravity going to start doing to it now? Pulling it down this way. Oops, should change that to red. Right? And it will speed it up by the same amount that it slowed it down on the up trip. Does that make sense? Okay. That's a little bit later on, but it's definitely a good intro. Okay. Good there. All right. So let's write down a couple of things, make sure we got that stuff here. All right. So we just described the motion of the object experiencing that acceleration. This number is so important that we refer to it as lowercase g. It gets its own value. So anytime that we talk about the acceleration caused by gravity, we just shorthand write that as lowercase g. That value comes up a lot because it affects almost everything that we do. Gravity is always acting on objects. It causes them to change what they're doing by this same amount every second. Okay? And we just kind of looked at a situation where it might not be a whole second, but it still changes the velocity of the object by some proportion of this relative to 1 second. Right? But this only applies when gravity is the only force or the only thing affecting the motion of that object. This applies only when gravity is the only thing affecting the motion of that object. For example, a demonstration that most of you have probably seen before, but so book, paper, right? If I drop them, which one's going to hit the table first? Paper hits the table. But if I take this same book and this same paper, right? But now I do this with the paper, right? Now I drop them. What did we see? Same time, right? Okay?
The book actually did first.
Does that mean?
The book should be what hit first.
No. Because in the first example, right, when I dropped the book and the piece of paper, gravity wasn't acting differently on those two things, because we talked about that gravity affects all objects the same way, but gravity wasn't the only thing affecting the motion of those objects, right? The paper has to deal with what? Air resistance and friction and those kind of things, right? But if by crumbling up the paper, I reduce the effects of those friction and air resistance forces, not get rid of them, but reduce them to a point where now they're not as prevalent on the motion of that object, and now we can see that effect of gravity. Okay? Good there? Okay. So, we'll watch a little video here. This video is a whopping 2 minutes and 5 seconds long. I know. I'm asking a lot out of you guys to pay attention for that long. But, so we will watch the video and then we'll discuss a little bit. Towards the end of the video, I am going to do a demonstration in the room that mimics something that is going on in the video, and we can talk about that at the end, okay? The sound on the video is really kind of quiet, so I have to turn the speakers up, and it makes the buzzing noise, so sorry about that. It's only for 2 minutes. I don't know what it's going to sound like on the recording, but I guess we'll see. So. All right. Here goes nothing. All right, here we go.
In this demonstration, we're going to show the effect of air resistance. If we drop a penny in a feather in a chamber filled with air, you do just as we expect. The penny hits first, and the feather falls later. This is because the feather was on the roll of an airplane, so it's floating on a cushion of air, like a parachute. But if we remove the air from the chamber, in effect making it a vacuum, then we get something entirely different. When we drop the penny and the feather this time, you see that they fall neck and neck simultaneously, and they both will hit the ground at the same time. All objects, no matter how big, how small, how light, or heavy, will increase in speed as they fall, gaining 32 feet per second each second.
In case that happened
If
too
we
fast
slow
for
this
you.
down, we can see
Instant replay.
Penny and
So,
the feather side by side, both increasing in speed together, and both reaching the bottom of the chamber at the same time.
How do you get the air
This
out?
is the law of falling
Vacuum pump.
objects. Once again, it doesn't make any difference
it?
how big or
No.
how small the object is. If
Why
the
is it
neglect
always
is
the
set to
outside
do it,
choice?
it all falls at the same
Ask
rate.
this at the end. So.
When astronaut David Scott in Apollo 15 walked on the moon, he thought that this would be an excellent demonstration to show.
With my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of the gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings on the moon. You know, drop the two up here and hopefully they'll hit the ground at the same time. How about that? Well, my guess is that Mr. Galileo was correct in his findings.
Okay. So first, Bechtel. Going back to this part of the video, right? So here, they kind of showed you the air gauge. They just take the air out of the tube inside. But because it's pretty much, right? Probably not all of it, but a lot of it. But the glass is rigid enough that it doesn't crush underneath the pressure from the outside atmosphere. If the outside container wasn't as strong, then we would see that the bottle like crushing in on itself. Like when you put if you ever put like an empty pop bottle, like you leave it in your car overnight and you come back in the morning and it's like crushed down, right? Try it sometime. So like an empty like a plastic bottle.
Yeah.
They from a vending machine.
Like a vending, yeah, like from a vending machine.
And you just leave it in your car.
Empty?
Why do
Yeah.
you leave it in your car?
Overnight. It gets
But why
cold.
your car?
It gets cold.
Oh,
Right, yeah,
just like
so,
if you
yeah,
leave it outside?
yeah, the temperature change will cause changes in the pressure as well. So yeah, you can leave it outside too, though. Or have you ever taken a water bottle on an airplane before?
A what?
A water bottle on an airplane?
Oh, I've opened up like a thing of like this thing of Purell on the airplane
Yeah.
once, and it like wouldn't stop coming on. I'm like, oh my gosh, it's all over.
Right. So it just changes the pressure, but the glass container that this is in is rigid enough that it doesn't crush underneath the lower pressure. Okay? But more to this point here, okay, that when we talk about the feather and the hammer, so we saw in the video that the feather and the hammer both hit the ground at the same time because we don't have to contend with that atmosphere issue that on the moon that we do here on Earth. But the demonstration that I did, though, what did you notice about the book that I dropped versus the hammer and the feather? Yeah. All right. See if I can get a book fast enough to do this. All right. Oh. So, it is true that gravity, oh, not this one. It is true that gravity accelerates all objects at the same rate, but gravity is different at different locations. So all objects on the moon experience the same acceleration. All objects here on Earth experience the same acceleration due to gravity, but not necessarily the same in both places. Okay? So, that being said, let's go here.
Question.
Good.
If you're on the moon,
Yep.
and you try to do a flip,
Yep.
will you be able to, or like just because when you're in midair you would rotate slower?
You would not necessarily rotate slower. You'd actually probably rotate faster. Okay? But that's
Did you float?
okay. Now let's talk about that. Okay, so going back to this is where the questions get good when we start talking about these things. So let's go back to this situation. All right? We throw this ball up into the air. If I throw this ball at 9.81 meters per second, here on Earth it takes 1 second because the acceleration is this much, right? The acceleration, it's all separate. Man, whatever. The acceleration is, I want that to stay together as a group, but, so, the acceleration is that much, meaning that every second that goes by, that's how much the velocity changes, okay? The acceleration on the moon is about 1.6 meters per second squared. No, I'm just doing it for the sake of this demonstration. Okay? So, in the time it takes Earth's gravity to slow this ball down from 9.81 to 0, okay, 1 second. After 1 second on the moon, the velocity of this object would still be, at t equals 1, on the moon, that object would be going about 8.2 meters per second. Still. Does that make sense? I'm pretty sure it doesn't make sense for some of you.
No, I get it. I'm really good. I was in conceptual physics.
Okay, sorry, my bad. I forgot about that. So. On the moon, the gravity only changes the velocity by this much every second. But in order for the ball to stop, what does its velocity have to end up as? At the top, it has to be 0, right? Because that's when it hits the top. So in 1 second, it takes the Earth to go from here to here, from 9.81 to 0 on the velocity. On the moon, it's still going this fast. So what is it still going to be doing? It's still going to be going up, right? For another about 4 more seconds. 5 more seconds. Gravity on the moon is about 1/6 of the gravity here on Earth. So, Anthony, if you do a flip, the gravity isn't going to affect the rotation so much, but it is going to affect how long you're in the air, because it takes gravity on the moon a lot more time to slow you down and then speed you back up on the way back down. Does that make sense? Okay.
How hard did you have to jump to get out of you jumping hard enough to be able to keep floating?
Yes, although that's a topic for a different day. So that's something we refer to as escape speed, and we're not ready for that just yet.
I
So,
finished that.
yeah, except for Maxie, maybe he's ready for it. But yeah.
Yeah, he understands. Don't make me.
Cal, question. Go ahead.
Have you seen the movie Gravity yet?
I have not. I'm kind of curious, just because I want to see. I want to critique it from a factual sense. You know.
Field trip.
So, you know. Maybe that'll be our exam for this unit. You have to go and write a paper
No,
critiquing.
that can be our.
Paper,
Oh, me too.
Nix the paper.
Just go to watch the movie. So, yes, Bethel.
That's field
Wait,
trip.
is this gonna, is it like, I don't know, if we're a professor at all classes, like, if we get A's in both quarters, we not have to take them
Only for the final exam.
only for the final?
Yeah.
And
So.
it's just third, fourth quarter?
Yeah, it's 3rd and 4th quarter. Yeah. So. That's tough to do. That's tough to do. You know, it's 3rd and 4th quarter. You know. So. All right. Next. All right. Here's what I want you to do next. I'm going to take this ball. I'm going to throw it in the air, just like this. That is an important number, yes. All right? So, that's the answer to everything from this point forward, just so you know. As long as you say 9.8, you got it. I mean, you got at least a 50-50 chance of being right, so, you know. Not really. So. I know I said that on the recording, but I'm telling you, that was a joke on the recording, okay?
No, it's not.
So, here's what I want you to do. Take this ball, I'm going to throw it up in the air, just like this. I want you to sketch for me a graph of position versus time, velocity versus time, and acceleration versus time. So 3 graphs: position versus time, velocity versus time, and acceleration versus time. This will probably be easier to do if you talk about it with the people around you, and you may feel free to do so. Discuss. position versus time, velocity versus time, acceleration versus time.
I know it's right, guys, because I'm an analyst. Just last second, I check that out.
Two of them look kind of right, one of them not so much.
It's the middle one.
I think the middle one's not right. So.
Knew it.
2 out of 3 look pretty good.
Do what?
But that's like not bad.
2 out of 3. I mean, Meatloaf wrote a song about that. So you know. So.
2 out of 3.
That's the song that Meatloaf wrote. Yeah.
Well, what happened? Oh, wait, this is.
Jesus, I don't know what velocity is.
Oh, you want to?
God.
Oh, wait, that's
All right.
Yeah. From the moment it leaves my hands to the time it gets back to my hand. So, not me throwing it, just from the moment it leaves my hands to the time it gets back to my hand. Yeah, from the moment it leaves my hand to the time it gets back to my hand. All right.
I knew it.
So, these pictures up on the board represent the position graph, the velocity graph, and the acceleration graph for this ball as I throw it into the air. On one condition. On one condition. If I take this, I grab it here. Okay. Where's the reference point in this problem? Yes, where is it physically in the situation of me throwing this ball into the hand? Okay? That's my hand, right? But we said that we have to establish. That's terrible. Yeah, right? We have to establish, right? Yeah. It's an industrial accident.
It looks like the pinky and the ring finger got like chopped
Yeah, they
off.
got that's what happens like if you don't be careful around machinery. So, not only is this a physics lesson, it's also a public service announcement.
Doing good for the society.
What?
You're doing good for the
I
society.
try. You know, that's why I'm here, really. So, yeah. So we have to make ourselves a reference point, but we also have to do what? So we have to make ourselves a reference point, but we also have to do what?
Directions.
Right? So which way is which in this problem?
Positives up,
Positives up,
negatives down.
negatives down. Which is generally how we set this up, right? Ball goes up in the air, right? Ball goes up in the air, and then it comes back down, right?
Your thing still, I think the graph's locked as well.
Anyway, so that ball goes up, right, and then it comes back down. That's the position. And we talked earlier this week about why the position graph is curved, right? Because an object that has changing speed, the slope has to change. On the velocity graph, right? What's happening on the velocity graph? Apparently that's not showing up on top. It's just,
Wait, why is the other one down?
hold on a second.
Because you hit it. Gravity is on. You put it above, you idiot.
So,
It's above. This is the one.
ah,
This is the graph.
Bechtel, that's a good question, okay?
I noticed.
Can I explain it?
Well, let me do it. I can get paid for this. So, Bechtel, what's causing all of these changes to this object?
The gravity.
Gravity, right? And which way does gravity pull on things? Downward, right? So this arrow is representing the pull of gravity, which is which direction
Negative.
in this graph, our negative direction, right? Does it matter whether the ball is going up or down?
No.
Gravity's always pulling on it which way? Downward. When the ball is going up, right, and gravity pulls down, what happens to that object? Because we have a positive velocity, but a negative acceleration. But on the way back down, right, which way is the velocity going now? On the down trip, the velocity is negative, but gravity is still pulling it which way? Negative. So if we have a negative velocity and a negative acceleration, what happens to the ball in the downtrip? Speeds up. Okay? So, Bechtel, the acceleration is always negative because it's always being pulled down by gravity. The change is always negative, but sometimes that causes an object to slow down, sometimes it causes it to speed up.
But it's still always gonna be negative.
The acceleration is always negative, right? That doesn't, this is, remember, the acceleration is the change. The pink line is what actually is happening, right? Because the pink line is velocity. So during this section, right, what's happening to the velocity during that section?
Slow down.
Because it's getting closer to zero, right?
You have to release your hand.
Right.
It's pushing.
But then this section, right, what's happening to velocity during that section?
Zero is when it hits the highest point.
Right.
It stops and then speeds up.
Right, but now it's speeding up which way?
Negative.
Negative. All right. Check out the calendar for the homework for the weekend, and we'll pick up this discussion on Monday. Good questions today, everybody.
I'm gonna check